Hi, my name is Joe Neer, and I'm going to tell you about some work that we've been doing on a system called Chorus for enforcing differential privacy. This is joint work with Noah Johnson, Joseph Hellerstein, and Don Song. So Chorus is really all about building systems that can cooperate with an existing database management system to give you differential privacy. So in this talk, I'm going to give you an overview of how that works. I want to start by giving a little bit of background about differential privacy. So differential privacy is a definition, a formal definition in math, of what it means to have privacy. The definition basically says, imagine you have two databases, and so we'll call our first database D1. Now imagine that I take that database and I add my data to it to get a database D2. Okay? So databases D1 and D2 are exactly the same, except that D2 has my data, D1 doesn't. Now if I run the same mechanism on both databases, I'm going to get two answers, answer A and answer B here. Answer A is calculated without my data, answer B is calculated with my data. What differential privacy says is, if the mechanism M satisfies differential privacy, then these two answers should be indistinguishable from one another. What that means, it means you can't look at the answers that that mechanism gives you and determine from the answer, did I participate in the study or not? And if the adversary can't determine from the answer whether or not I participated, then that means the adversary also can't learn anything else about me. They can't learn my age or my name or my address, stuff like that. So how do you get differential privacy? The common strategy is to add random noise to things. So you have some query you want to run on the data, you add some noise to the output of that query, okay? And in a lot of cases, this is pretty simple. So I can write a little Python program, for example, that, say I have this database that's just actually a list of random numbers, and say I want to know how many numbers are in the list, right? I can get differential privacy for that answer by adding noise to the result, drawn from the Laplace distribution, where the scale of the noise is 1 over epsilon. And epsilon here is called the privacy parameter. You might also have heard this referred to as the privacy budget, and it kind of allows me to tune how strong the privacy is. So the smaller epsilon is, the stronger the privacy guarantee is. And so I can add this noise to the result of this query, and the answer that I get is differentially private. If I run this multiple times, I'm going to get different answers. Okay? The kind of story behind Chorus is that starting back in 2016, we had this collaborative research project with Uber. And Uber wanted to be able to build a system that would allow them to query customer data without revealing information about specific customers. Uber had some issues with this in the past. But one of the major challenges was that they had a lot of data, and anything we could build that would be custom would actually probably not scale to their data. And so one of the requirements really was to be able to reuse all of the infrastructure that Uber had already built, and to be able to layer a solution for differential privacy on top of that infrastructure. And so what we did is we built a tool called Flex that is completely post-processing based. So you have the existing database run the query, and then you have the Flex tool add the noise after the query is finished running. And this scales up great because you don't change the database. The problem is that there are a lot of kinds of things you might want to do with differential privacy that you can't do using post-processing by itself. And this was really the motivation behind the Chorus system, and it's the improvement of Chorus over something like Flex. And a good example of this is summation. If you want to sum up a list of numbers instead of just count how many things are in the list, then the amount of noise that you have to add has to take into account how big each of the numbers in the list could be. And the way that we typically do that in summation queries is by clipping. So we take all those numbers in the database that we want to sum up, and we clip them. We force them to lie within a specific range. And now I can add noise scaled to the kind of size of the range that I have clipped to, divided by my privacy parameter epsilon. Now the problem with this picture is I had to do the clipping before I did the query. Okay? And so I can't do the clipping as part of my post-processing. And it turns out that this is really, really common in differential privacy. So summation is one simple example of this, but there are a whole bunch of algorithms out there that are way more complicated than summation that some of them are iterative, they have loops, and they add noise to things multiple times, and over time they try to improve the differentially private estimation that they're making. And these kinds of things, you just can't do them with post-processing. And so we wanted to build a system that could retain the benefit of Flex, the ability to work with an existing database, but also be able to support some of these more complicated algorithms that you can't do with just post-processing alone. Okay? And so the key insight of Chorus was we need to be able to have cooperation between the mechanism that adds the noise and does other things like clipping and the database management system itself. Okay? And we'd like to be able to do that without actually modifying the database. So the Chorus system really has three major components. The first one is a component for rewriting queries. So if you have to do something like clipping before the query actually runs, then this component helps you rewrite the SQL query that's coming into the system so that the database can actually do that clipping for you. The second component is analysis. Remember I said we had to scale the noise differently for that length query versus the summation one. The analysis piece actually does abstract interpretation of SQL queries to figure out what is the scale of the noise that you have to add to the particular query that you're running. The third piece is a post-processing piece, and this is really just a library of functions for adding noise to things. So first, in our summation query, first we did clipping, then we did the query, and then we added noise. So the post-processing piece of Chorus gives you library functions for generating and adding that noise. So here's an example of a mechanism written in Chorus. Our first step is to rewrite the query to perform clipping, just like we did in our summation example earlier. The second step is to run an analysis that determines the sensitivity of the clipped query. The third step is to actually run the query using the database management system, and here we're running the modified query that has the clipping built into it. And then the final step is to use post-processing to add noise to the result. Okay? So this actually implements pretty much exactly what the Python program that I showed you earlier implements. The difference is that this mechanism actually cooperates with an existing SQL database to help you do the heavy lifting of this query in the database system itself. We actually did some experiments on some of the production data that was in use at Uber. What we found is that for simple algorithms that make very small changes to the way the query runs, for example, the summation example that I showed you, the overhead tends to be very small compared to the query without differential privacy. For more complicated mechanisms, things get a little bit worse in terms of overhead. And this is kind of inevitable because some of these complicated algorithms for differential privacy are actually doing a lot more work than the original query would do. And this is one of the questions that we still have is, to what extent can we use the features of Chorus to kind of ameliorate some of the additional overhead that pops up when you use some of these complicated algorithms for differential privacy. So to conclude, I want to come back to this idea that this cooperation between the Chorus system and an existing SQL database, is really the key insight that I think has enabled us to be able to implement some of these really complicated algorithms for differential privacy in a way that scales up and reuses a lot of the existing scalable infrastructure that people have built for querying data. It turns out a lot of the things that are basically impossible to do with post-processing alone and basically impossible to scale up by writing a little toy Python implementation, it turns out that if you reuse the existing infrastructure that you have for running queries, that you can run those algorithms with no problems. They scale up just fine. Another thing I want to mention is that we've open sourced the code for Chorus, and I encourage you to take a look at it. You can also find a link to the paper at this link. And if you have any questions, I'm happy to answer them. And I'm always happy to answer questions and engage in more discussion via email. So my email address is here on the screen as well. And thank you so much for your attention.